Good morning, students. Let's begin today's new lesson. In this lesson, we will learn integral program model. The integral program model is a little different from LP program model. In these lessons, we discuss two topics. Section 1, prototype example, introduce what is integral program. Section 2, formulate with binary variables, introduce why we use binary variables to formulate a model. Introduction. In many practical programs, the decision variables actually make sense only if they have integral values. For example, it is often necessary to assign people, machines, and vehicles to activities in integral quantities if requiring integral values is the only way in which a program deviates from a linear program formulation, then it is an integral program. The mathematical model for integral program is the linear program model with the one additional restriction that the variable must have integral variables. If one sum of the variables are required to have integral values, this model is true as mixed integral program. One distinguishes the all-integral program from this mixed case. We call the former pure integral program. This is mixed integral program. This is pure integral program. Mixed program is some is integer and some is only real number. Pure integral program, all the decision variable is all integer numbers. However, another area of application may be of even greater importance, namely programs involving a number of iterated yes or no decisions. In such decisions, the only two possible choices are yes or no. For example, should we undertake a particular fixed project? Should we make a particular fixed investment? Should we locate a facility in a particular site? With just two choices, we can represent such decision by decision variables that are restricted to just two values, say 0 and 1. Thus, the yes or no decision would be represented by, say, xj such that we set xj equal to 1 if decision j is yes, equal to 0 if decision j is no. Such variables are called binary variables or 0-1 variables. 0-1 variables. IP programs that contain only binary variables sometimes were called binary integer program. We denote by BIP. Now we introduce section 1, prototype example. The California manufacturing company is considering expansion by building a new factory in either Los Angeles or San Francisco, or perhaps even in both cities. It also is considering building at most one new warehouse, but the choice of location is restricted to a city where a new factory is being built. The net present value of each of these alternatives is shown in the first column of the table. First column of the table. This is decision variable. Decision variable. The rightmost column gives the capital required for the respective investments, where the total capital available is $10 million. We see in this table, the decision variable is x1, x2, x3, x4. Means x1, build a factory in Los Angeles, yes or no. x2 means build a factory in San Francisco, yes or no. x3 means build warehouse in Los Angeles, yes or no. x4 means build warehouse in San Francisco, yes or no. And if you build a factory in Los Angeles, its need capital is $6 million, and we get $9 million net present value, and so on. And the last law is the available capital is $10 million. In this program, the objective is to find the feasible combination of alternatives that maximize the total net present value. Now we set up this program model. First, to determine the decision variable. In this table, the decision variable is in this column. So in this program, we have either or 4 decision variables, x1, x2, x3, and x4. Now we write the objective function. The objective function is to maximize the net present value. And this is the each project net present. So we use these numbers to time these variables. We get the objective function is. The objective function is maximize z equal to 9x1 plus 5x2 plus 6x3 plus 4x4. And this is the objective function, the total net present value we need to maximize. Now, the constraints in this program, the first is capital variable. Capital variable, we only $10 million. Now we think about the constraints in this program. We notice that the first constraint is the capital limited, and we know in this table the capital available is $10 million, and we need the capital is 6 million, 3 million, 5 million, 2 million. So we use this column number 2 times decision variable. We get the left of this equation, and this is the used capital. Less than the available capital is 10 million, and this is the first constraint. The second constraint is building at most 1 warehouse. In this program, the restriction is emphasis that building at most 1 warehouse. We note in this table, x3 and x4 can express build warehouse. So at most one, that is in each true variable, at most 1 is equal to 1. So we write as x3 plus x4 equal less than 1. This is the second constraint. And the third constraint is the choice of the location is restricted to a city where a new factory is being built. That is, if you build warehouse in Los Angeles, you must first build factory in Los Angeles. If you build warehouse in San Francisco, you must first build factory in San Francisco. So we write as x3 less than or equal to x1, x4 less than or equal to x2. This inequality express the choice of location is restricted to a city when a new factory is being built. So we summarize the model of this program as this model. And we notice that in this model, the decision variable is all binary variable. So we call this model is BIP model. In this model, we noticed that, like the second pair of decision of this example, group of yes or no decisions often constitute groups of mutually exclusive alternatives, such as only one decision in the group can be yes. This is the mutually exclusive constraint. That is, only one can equal to 1, and the other is equal to 0. Each group requires a constraint that the sum of corresponding binary variable must be equal to 1 or less than to equal to 1. Occasionally, decisions of yes or no type are constraint decision. Constraint decision, that is, decision that depend upon previous decision. In this model, this is the constraint decisions. It means if x3 equal to 1, that x1 must first equal to 1. That is, means if we built warehouse in Los Angeles, we first built factory in Los Angeles. You have just seen a prototype example where the basic decision of the problem are of yes or no type, so that binary variables are used to represent these decisions. We now will look at some other ways in which binary variable can be very useful. In particular, we will see that these variables sometimes enable us to take a problem whose natural formulation is intractable and reformulate it as a pure or mixed IP problem. So we introduce section 2, formulation with binary variables. Add all constraints. Consider the important case where a choice can be made between two constraints, so that only one add one must hold, whereas the other one can hold but is not required to do so. For example, there may be a choice to which of the two resources to use for a certain purpose, so that it's necessary for only one of the two resources availability constraint to be held mathematically. To illustrate the approach to such situation, suppose that one of the requirements in the OO problem is that in the problem, either this constraint is held or this constraint is held. Maybe this two resource is replaced. For example, we can produce the products in plant 1, and we can produce the products in plant 2, but this two plants is replaced. So at least one of these two inequalities must hold but not necessarily both. This requirement must be reformulated to fit it into the linear program format where all specified constraints must hold. That m is a very large positive number, generally is infinitely larger, then this requirement can be related as. We notice in these two inequality. In the right, we plus my. M is a very large number and generally infinitely. In this inequality, we plus m times 1 minus y. And we notice in this equality, if y equals 0, we notice two inequality is the first one is held. And the second is not held. If y equal to 1, otherwise, the second is held, the first is not held. So we realize either one or one choose in 2. Case 2, k out of n constraints must hold. Consider case where the OL model includes a set of n possible constraints such that only some k of these constraints must hold. Only some k is held and other is not held. Part of the optimization process is to choose the combination of k constraints that permits that objective is to reach its best possible value that n minus k constraints not chosen are, in effect, eliminated from the problem. For example, if we have constraints of f1 less than or equal to d1, and these constraints, and they are unconstrained in this program, but we need k to hold. So we write as plus my1 plus my2 plus myn, and at the constraint is sum from I to n yi equal to n minus k. This equation means that only ky is equal to 1. So in this n constraint, we have k constraint is holder. Case 3. Functions with n possible values. That is, if in the program they are functions with discrete number, consider the situation where a given function is required to take on any of n given values. That is, f x1, x2, and xn equal to d1 or d2 or dn. For example, f equal 1, 2, 3, or 4, and so on, and so on. And this is unusual constraint in the program. So if we write these constraints in the general constraints in the program, the equivalent constraints we write as f x1, x2, xn equal to sum from I to n di yi, and sum I from 1 to n yi equal to 1. We notice that in these constraints, if yi equal 1, that's f is equal to di. If yi to equal 0, then f equal to other numbers. So this new set of constraints would replace these requirements in the statement of the old program. First case is fixed charge program. It is quite common to incur in fixed charge or setup cost when one is undertaking an activity. For example, such a charge occurs when a production run to produce a batch of particular product is undertaken, and the required production facility must be set up to initiate the run. In such cases, the total cost of activity is sum of a variable cost related to the level of activity and the setup cost required to initiate the activity. Frequently, the variable cost will be at least roughly proportional to the level of the activity. If this is the case, the total cost of activity can be represented by a function of the form. The total cost include fixed cost and variable cost. Fixed cost is not related to amount of production, and variable cost is proportional to the amount of production. And this function is a piecewise function. And it is also ungenerally constraint. So we rewrite this constraint as Cj xj plus Kj yj, and yi is binary variable. We notice that in this model, if yi equals 0, then it not have this fixed cost. And if yi is equal to 1, then this model have this fixed cost. And in this inequality, we can notice that only if yj equal to 1, xj may be greater than 0. If yj is equal to 0, xj must be 0. That is, the product j is not produced. So in these lessons, we have introduced binary variable, how to reformulate the model of integer variables, and the binary variable is very important in set up a model. Thank you very much.